Okay, so this is Chem 101, Fall 2015, and I'm going to go over the creation of the snazzy FTIR workbook. Alright, so the workbook should look like this, and it should have some cool functionality, such as the ability to adjust the frequency cutoff of a low-pass filter, and then the ability to run the forward and reverse Fourier transforms on buttons, the ability to change or to invert our filter from low pass to high pass, and then we can run our inverse transform there on that. And coming back down here, and then we can re-invert that filter and run the inverse transform again. We can change to a different type of function. We can change to a square wave function here, which is now drowned in noise. We can run the forward transform on that baby. You can see there's the square wave, there's the noise peaks, and then run the inverse transform. And there is the original signal, there is the filtered signal. So obviously the square wave has some high frequency components, so it's compromised a little bit by reducing all these frequencies, by zeroing out all these frequencies, but it can still be recovered fairly clearly. Okay, so there's a lot to do. There's a lot of cosmetics to take care of, so this is going to be a fairly long video, and I'll try to edit it to speed up the boring bits and hopefully cut out the bloopers, but for the time being, I'm just going to get started here, and I'm going to start on this completely blank worksheet called Book 1, and I'm gonna save it as the Fourier model workbook.xlsm. Fourier example 3.xlsm. Okay, I'm going to make sure and save this as a macro-enabled workbook, and save it right there. Okay, so here we go. I'll make a small column A. I'm just copying from my other workbook, and now I'm going to put in some variables. So there's dt here, tmax, pi, and NPTS, our number of points. And then now we're going to define our noise, and noise is going to have frequency 1, frequency 2, NS1 and NS2 for the amplitudes, and then there's going to be signal, and the signal is going to have amplitude 1, mean 1, and standard dev 1, and amplitude 2, mean 2, and standard dev 2. Okay, then on to filter. And filter is going to have invert, and then there's going to be a button there. It's going to leave a couple spaces for the button, and then actually, hold on, so there's filter and low pass, and then filter type, and leave 2 spaces for that button. There's invert, and make that guy true, and then there's 2 spaces for the invert button, and then there is low pass again, and then frequency. That's going to be the cutoff for the filter. We're going to leave 3 spaces for a spin bar, and we're going to put our cutoff value there. And we're going to have 2, 3, 4, 2, 3, 4, 5, and now we're going to put our select function variable there. And okay, so I think that's all of our variables. So for dt, let's put, okay, for dt, that's going to depend on a couple of other things. So Tmax we can define as, say, 32 seconds. Alright. Pi is 3.1415927. And endpoints is going to be 512. The noise frequency one, let's make it 20 hertz and 10 hertz, and then amplitude of 5, and oops, sorry, got these in the wrong places here. Amplitude of 5 and 2.5. Okay, down in the signal, amplitude 1 is going to be 50. Oops. 58 and 1, and 115 and 1. And then the filter low pass, not exactly sure if we're going to do anything with that. Invert is going to be true to start with. And then the cutoff, let's say make it 25. And then the select function, we'll make it 2, just to give these some initial values. Okay, so now let's go ahead and just start in the beginning here. Let's make a nice big label here. 1 through 6 out through O, and we're going to merge these cells, and we're going to put in some big text here that says, let's see what font size is this in. This is in 22-point Calibri, so, and it's going to say here an illustration of the discrete and a light blue exterior. And I'm going to put a light border around it. There we go. Okay, alright, so now there's the title. So let's go ahead and put in the definition for dt. And dt, as you see over here, is equal to Tmax over NPTS. Okay, so those are defined functions. So let's go ahead and go to Formulas, Create from Selection. It's the left column, and we're going to go OK. Alright, now here are the noise definitions. Create them from that selection. Here are the signal definitions. And there's the word invert. There's the invert function. And there's the cutoff. And we create that from the selection. And then there's cell function here. Okay, cool. So we're cooking with gas. We're just going to keep going here. By these guys to make them look good. A box. And I'm going to make the noise and the signal, give them outside borders. Outside, outside. Going to make them light green background, boundary. And then this guy is going to have a boundary, I think. 6 seconds. That's a 16th of a second for 32 seconds, and total of 512 points. Alright, so let's define a few things. We can go down here and we can put our index here. Okay, and this index is going to go from 0, 1, 2, like that. Let's get it started. And then we can, I don't want to do that, do I? No, I just want to drag it down until it says 512. 2, 3, 4, 10, 11, and 12. There we go. Actually, since we're including 0, we want 0 to 511. Okay. Control up there. So this is our index group. Okay. So index here, it's going to be clear. And actually I'm going to extend this merge down there. I'm going to put a boundary around that. And then I think I'm going to put a boundary around that. An outside boundary. Okay. Good. Now we're going to define the signal abscissa here. Signal is going to be in the time domain, and there's going to be signal plus noise here. Okay. And these numbers are all going to be real numbers. Okay, so now the time signal is going to be defined as going to equal the counting number times dt divided by npts. Okay. Now when this guy goes down, it's going to give us too many sig figs here, but I'm going to get those a little under control there. Okay. Now, let's see here. Now, once we get to the signal, we're actually going to use some VBA here to define the signal. So I will get to that. Okay, to do the signal, we're going to use Visual Basic, and we're going to come over here to our Fourier example, and Fourier example, that has everything in it. And so what we're going to do here is we're going to insert a module. And this module is going to have a VBA function called SEL-FN. Okay, so SEL or select FN for select function will take as an argument SEL as an integer argument called SEL, and a real number or a double precision real number as x, and it's going to return a double precision number, right? And this used to be very simple. It used to be amplitude times the norm dist of the number, mean standard deviation of 0, mean standard deviation of 0, right? But since I want this to be modular and to be able to switch between different functions using the touch of a button, then what we need to do here is to pass a lot of information between the spreadsheet and the VBA function. So I'm going to define variables that are local to VBA here as amplitude 1, amplitude 2, mean 1, mean 2, standard deviation 1, standard deviation 2, Tmax, T1, T2, and T. And then I'm going to get these from the worksheet. Amplitude 1 is going to be the range of the variable name, spreadsheet variable name amplitude 1 dot value. And this takes the cell in the spreadsheet named amplitude 1 and returns its value. And that is readable by VBA, etc. for mean 1, mean 2, standard deviation 1, standard deviation 2, Tmax, etc. Right? And T1 and T2 are useful down below. Okay, so cell is an integer, right? So we're going to choose what to do dependent on cell, and that's called select a case. This is basic syntax here, right? So we're going to say select case SEL, case 1, that is when SEL equals 1. And that implies we're going to do Gaussians. This green text is comment. In this case, T is going to be the amplitude 1 times the norm dist. You actually have to use worksheet function dot norm dist of x, mean standard deviation 0 plus amplitude 2 times worksheet function norm dist of x, mean 2, standard deviation 2, right? Otherwise, we're going to feed it a square wave, which is going to be we're going to divide the data set up into 4s, and then so T1 is Tmax over 3, so we're divided into thirds. And so if the x value is between T1 and T2, the first and third thirds, then it's going to be 1, otherwise it's going to be 0. And then any other integer that gets passed in is going to return a 0. Okay? Then SEL FN is going to return the value T. A little bit of a long explanation, but there it is. And so there's SEL, select FN is going to be in module 1. Okay? Alright, and I think everything is operating for that function. So the signal, we're going to put in for the signal here. We're going to put here equals select FN of, fn, lowercase n, of, and we're going to use the select fn value here, and then the time point in E15. Okay. Now that is select fn value is 2 right now, so this might be returning a square wave. I'm hoping. So it's returning zeros everywhere. Just see what's going on there. So let's make this a 1. So now looks like we're probably getting Gaussians here. Very extremely tiny Gaussians, evidently. Okay. So a little bit of debug time here. Okay. So case of 1 is Gaussians. Amplitude 1 times the norm dist plus amplitude 2 times the norm dist. Let's just see what amplitude 1 is. 2, mean, standard dev, amplitude, mean, standard dev. Not quite sure why that's coming up with such small numbers there.
Yeah, I took
They're all 10 to the minus 13. I think it may have to do with the fact that the the mean value is misplaced here. So I actually want the mean value to be within the time of the impulse. So time is not. No, I see you shouldn't be dividing by num points there. We just want that.
I love chemistry. I love chemistry. I like the
there we go. There we go. There we go. Alright, so now that looks correct. And then signal plus noise. Let's see what to put in there. That's going to be, this guy here is going to be equal to the signal plus NS1 times the sine of frequency 1 times time plus NS2 times the sine of frequency 2 times time. Okay. And we'll let those guys go down. So now what I'm going to do is I'm going to create a color coding for real and imaginary numbers. Okay. Now we have our signal, time, our signal, and our noisy signal. Now I'm going to say, well, what is this going to be there? This is going to have sort of a green background here. Okay. Now we'll phase that. Okay. Put some outlines around these guys, outlines around that guy, and outlines around that guy. And I'm going to make all these numbers into green numbers. Okay? So these are real numbers here. Let's see what these real numbers look like. Let's make a graph. And I'm not going to do it that way. It's kind of stupid. When I say signal time, and then I'm going to say control, shift control arrow down. Okay, we'll see how this comes up. Now we'll go to insert, charts, there we are. So there is a noisy signal for you. And this guy, I'm going to name it signal plus noise. Make that guy a little bit smaller. Take that guy. Format those numbers. Labels, numbers, there we go. There we go, give them a general format, and then we can select that axis, go to those formatting options there, go to 32, I think it's the actual limit there, get rid of that stuff. Oops, not the whole thing. Get rid of of that stuff. And I think I'm going to leave it auto-scaled. Now I'm going to go to Design. Oops. Sorry, I think it's View. No. Page Layout. Align. Snap to Grid. I'm going to take these boundaries. I'm going to snap them to the grid lines. So I'm going to make it kind of small here because I'm going to stack up a number of plots here. Good. I'm going to snap this out to edge of column I. And there we have it. Here's our noisy signal. Okay. And I'm going to make this green just to color coordinate with the other stuff. Go solid line and make this baby green. Okay. All right. I'm going to outline it. Okay. Save this baby before I lose it, and take a break.